Okay, let's do one more limiting reactant practice problem. Okay, here's the scenario. In a lab, at standard temperature and pressure conditions, 578.44 grams of sodium metal react with 540.60 milliliters of water. And out of that reaction, 219.55 liters of hydrogen gas are produced and collected in a gas collection tube. The other product in this chemical reaction is sodium hydroxide. Okay, so this problem brings in liters of gas and moles of gas and that kind of stuff, so there's a little more to this problem. Okay, so the questions we're going to answer are, of course, to write the balanced equation and determine the limiting reactant, as well as determine the theoretical yield of hydrogen gas in grams and liters. And based on that theoretical yield, we're going to calculate our percent yield and percent error. Okay, so let's just take it from the top here to write the balanced chemical equation. So we have sodium metal, which is Na, reacting with water, H2O, to produce what we know for sure, hydrogen gas, and then it also says the other product is sodium hydroxide, NaOH. Okay, +1, -1, so that's a good formula. Okay, now here I'm going to make a recommendation to you guys. When hydroxide appears on one side of the equation here, like it does with sodium hydroxide, and water appears on the other side, the best thing you can do for balancing an equation like this is to rewrite your formula for water. I'll do this like so, as HOH. Okay, that allows the hydrogens and the oxygens not to have to split up, and we can balance the hydroxides against each other that way as a polyatomic ion. So I think that actually works pretty nicely. That's a pro move. Okay, so now we can just sort of go ahead and balance this. I'm going to do this quick. 1 sodium, 1 sodium, 1 hydrogen, 2 hydrogens. That means we need to double this side. 2 hydroxides, 2 hydroxides, 2 sodiums, and 2 sodiums. So that should be the balanced equation, all right? And of course, as with everything, we want to put the molar masses of these things right below their chemical formulas. Sodium, 22.99. HOH is 18.02. And then hydrogen gas is 2.016. I'm not gonna do sodium hydroxides because it's just not asked about in this problem at all. Okay, so let's figure out the limiting reactant here. One thing that I'll start with doing here is that when we have milliliters of water, which is a volume unit of water, as long as we're talking about water, 1 milliliter is equivalent to 1 gram. And so whenever you see milliliters of water, if you're more comfortable working with grams, just change the unit from milliliters to grams, okay? So I like to do that because we work with gram to gram stoichiometry. Okay, so I'm gonna take our given amount of sodium and I'm gonna see how much water it would take to react away all of the sodium. Okay, so we've got, how much sodium? Oh yeah, 578.44. That's grams of sodium with a molar mass of 22.99. And then the mole ratio between sodium and water is a 2 to 2. You can reduce that down to 1 to 1 if you want to. I don't do that though. And then water, 18.02, and that is 1 mole. Okay, so let's see how much water it's gonna take to get rid of all of that sodium. 578.44 times 2 times 18.02. That is 453.39. grams of H2O required. Okay, let's see how that compares with how much water we have to work with. So we need less than we have. Okay, so when less of chemical B is required than we have, that means chemical A is our limiting reactant. And so everything is going to be based on how much sodium we have. It's going to completely react away, and all of our so all the sodium goes away, and we have some water left over. Okay, so we're going to say here that sodium Na is the limiting reactant. Okay, so that question is answered. Okay, let's move on to the next couple of questions here. We are going to determine the theoretical yield of hydrogen gas in liters and in grams. So let's just do it in grams first, and then we can convert that number of grams into liters using our conversion factor at standard temperature and pressure. So again, the production of hydrogen is based on our limiting reactant, sodium, of which we have 578.44 grams of. Its molar mass again. The mole ratio this time between sodium and hydrogen. So that's a 2-to-1 ratio. And then the molar mass of hydrogen goes up here. So this is going to give us our theoretical yield in grams. Times 1 times 1 times 2.016 divided by okay, so that gives us 25.632 grams of hydrogen gas. That's our theoretical production of hydrogen gas. Now we're going to convert that 25.632 grams into liters by doing a quick calculation here. Remember, we go from grams to moles to liters, okay? So we got this many grams. The molar mass again of hydrogen gas is 2.016 per mole. And then we know that 1 mole is equivalent to 22.4 liters. That's at standard temperature and pressure, which was defined in the question. So let's figure out our theoretical yield in liters here. 25.632 times 22.4 divided by 2.016. Okay, so we get theoretical yield of 284.80 liters of hydrogen gas. Okay, so here's our two theoretical yields. This one in grams, this one in liters. Okay. And so let's then now find our percent yields and our percent errors. So here we got to go back to the problem and figure out what the actual production was in lab. Here it is. So we made actually 219.55 liters. That's our actual production. So remember that our percent yield is our actual over our theoretical times 100. So actual 219.55 over our theoretical liters, we'll do liters, 284.8, and then we're going to multiply that by 100. Okay, so 219.55 divided by 284.0 times 100, and that's a 77% yield. 0.8. Now, it doesn't, the problem doesn't ask here for the percent yield in grams or liters. I've just done the percent yield in liters with our actual amount of liters and then our theoretical amount of liters. So 77% yield. That you could do that same way if you use the grams, but you would just have to convert your actual production into grams as well. And then you could use grams to find this too, but why would you do that? And then finally, our percent error is our actual minus theoretical, absolute difference there, over the theoretical value times 100. And so let's take our, I'm going to do the bigger number first here, 284.80 liters that got theoretically produced, minus the actual production from the problem, 219.55. And then we're going to divide that difference by the theoretical 284.80. times 100, and that is going to give us our percent error, 284.80 minus 219.55, 65.25, good, divided by 284.80 times that number by 100, and we get a 22.91% error. Okay, so that's it. You can use limiting reactant and stoichiometry, with moles and liters of gas and all that kind of stuff. It just brings in a little bit more thinking for a problem like this. So, anyway, hope that helps.